Okay, let's get started tonight. I'm Ed Foley, the president of TAAA. Welcome, everyone. We've got members here in the room at our monthly meeting every Friday, the first Friday of the month, here at Stewart Observatory Auditorium. But we also have online members on Zoom, and we've got people visiting on social media. Tonight we've got a little bit different technical staff. We've got Bernie Stinger on the camera. Welcome, Bernie. We've got Jim Knoll joining us from Northern Arizona, who's helping run things. And of course, Terry Lappin, always reliably right here to help us with all of the things in the room. In order to start the meeting tonight, we have a member who is going to bring us a little bit of poetry. Is David available? David Levy, are you there?
Right here. He's right here. Can you hear me?
David, we can hear you.
Okay, great. Thank you so much, Ed. And congratulations on your becoming president. And best of luck and my deepest sympathy. So good to see so many friends of mine at the meeting tonight. And as I think all of you know, yesterday in our faith was Yom Kippur, which is a very special day. And one of the things we do is we remember those we have lost. I think there is not a person in this auditorium who has not lost a loved one, someone very special. And so for tonight's poem, I would like to quote Yesh Kochavim, a poem by Hannah Sinesh. There are stars up above, so far away we only see their light long after the star itself is gone. And so it is with people that we loved. Their memories keep shining ever brightly, till their time with us is done. The stars that light up the darkest night, these are the lights that guide us as we live our days. These are the ways we remember. Thank you, Ed, and back to you.
Thank you, David. Former President David Levy. Thank you. Tonight, our speaker is Sukrit Ranjan. And Dr. Ranjan is at the Lunar and Planetary Lab and investigates a subject that is fascinated humanity for, I'd say, hundreds, if not thousands of years. The question is there life elsewhere? And Dr. Ranjan is helping us to answer that question by investigating how we would tell. Sukrit, can you give us a clue as to how we would figure this out from such a distance?
Build really big telescopes. The eternal answer. Oops, that was not quite. Yeah, I think so. Okay. All right, is this whole we're just going to mute that. I think that'll be better for everyone. So thank you guys so much for inviting me out here. It's a real pleasure to be here. So as they mentioned, my name is Sukrit. I'm an assistant professor over at LPL, which means I'm in enemy territory right now. I'm gonna need you guys to run cover for me to get out of here alive. But in the meantime, we're going to talk about a little bit different kind of. We'll still be talking about life, but in a more planetary context. So yeah, so the thesis of today's talk, the big picture question that's motivating it, assuming I can get this thing to work. Not a great start. Okay. Yeah, we'll just do it manually. Okay. So yeah, the motivating question for this tonight's talk is basically life in the universe. So for as long as there have been humans, pretty much, we've been looking around and looking up and wondering, are we alone? This is a fairly fundamental question, and it's but one that we've actually engaged with in a serious scholarly way for at least 2,500 years, as far as we can tell. And actually, in a way, in something that's both kind of shocking and both kind of exciting and kind of disheartening, the arguments that were being bandied around 2,000, 3,000 years ago looked relatively similar to the state of the art that we had today until quite recently. So to illustrate this, I'm going to show you a quote from this guy over here, Lucretius. And it's this kind of, excuse me, sorry. It's this kind of neat little quote he has here. I'll just read it out loud because it feels surprisingly prescient. And if the force of nature remains the same to throw the wandering elements to and fro in the same way as here, it must be admitted that there are other worlds in other parts of the universe and other races of men and of wild beasts. And so this was written in the 1st century BCE, and it sounds fairly similar to what we have today. It's like he's basically making the argument, hey, if natural laws are the same everywhere, there's probably other planets out there, and if there are other planets out there, why aren't there other like beings like us out there? And so this is in some sense kind of exciting because it sounds very modern, but then if you think about it, it's also very sad because it sounds very modern, it means that we haven't had much progress over the last 2 millennia. So that's not the most optimistic thing ever. And so why is that? Well, the fundamental reason is that they didn't understand then, and what we do understand today is that space is really, really big. These other worlds are really, really far away and really, really hard to study. And so for a very, very long time, both of the claims being made by these philosophers based on purely the principle of mediocrity, the idea that if you select an item from a set, it's more likely to be representative than not, is that there are probably other worlds out there like Earth, and there are probably other organisms out there as well. And so this is a neat argument, but it's fundamentally a philosophical argument. There's absolutely no empirical reasoning in there. There's no data, there's no calculations, there's no evidence whatsoever. It's just, things are probably this way. And this is the way things, this was a kind of the state of the field for a very long time. And both of these claims, the first major change, as members of this group are well aware, came with the advent of this fellow over here, Galileo, who turned his telescope to the skies and discovered that the moons of Jupiter were not in fact points of light, celestial points of light, but were in fact circular objects that really looked like planets. It looked like they had rocks, they looked on them. They looked like they had surface features like mountains and craters and things. They did not look like they were made of immutable, ineffable, heavenly stuff. They looked like they were made of dirt, the same as we had over here. And so this was kind of our first evidence that the first part of what Lucretius said, there are other worlds out there, was in some sense correct. And after a little bit of an initial kerfuffle about what this meant, folks overall got super excited because then they started asking, well, if the first part of that clause now has empirical proof, what about the second part of that clause? These other worlds out there, are they potentially inhabited? And so here too, telescopes started giving us the first kind of empirical constraints. So once we knew that the dots of light up there, the planets in particular, were worlds, folks started putting better and better telescopes on them and started trying to see if they could see evidence for life on them. And as the majority of the scientists working on this, and indeed the philosophers as well, felt that the answer had to be yes, for basically the reason Lucretius outlined. And so this gave way to a little bit of confirmation bias, perhaps most famously in images like this one of the so-called canals of Mars. So this is a map. This is an image from one of Percival Lowell's maps, derived from his observatory up in Flagstaff. So Lowell had a pretty good telescope for the time. It was doing really the best he could. He was operating from one of the best sites in the world. And with that, he thought he was able to see evidence of structures on the surface of the planet, specifically long linear structures on the surface of the planet, which did not appear to be natural, didn't appear to be curvy in the same way most large-scale macrostructures are. And so he interpreted this as evidence of a technological civilization that was building canals at the surface of the planet. And he interpreted this as evidence that Mars was alive. And this was not a fringe view. It was in fact quite mainstream. The founder of my own department, Gerard Kuiper, writing as late as 1955, you can find papers he published in the APJ, doing measurements of what he thought was vegetation, seasonal cycles of vegetation, the pigmentation of vegetation on the surface of Mars. It was an extremely mainstream view throughout the telescopic age that Mars was not only habitable, but was inhabited. What stopped this whole vision dead in its tracks was the planetary exploration program. When NASA started spending spacecraft there, when NASA sent Mariner there, the first images of Mariner that came back completely falsified the blurry images that we were getting out of the telescope. So once you no longer had to contend with the atmosphere, once you could overcome those millions upon millions of miles and get images of the surface of the planet from orbit, it was immediately clear that the planet was thin, and the atmosphere was thin, the surface was frigid, and there was nothing alive there. And today we have these gorgeous rovers, amazing pieces of scientific art that are roaming the surface of the planet, and they reveal an amazing world. It's fascinating in so many ways. It reveals interesting aspects of dust physics. It reveals a really interesting geological history. It poses a major puzzle for climate modelers. But one thing that it doesn't reveal is any evidence of a habitable world. So there's no evidence of liquid water anywhere at the surface of the planet. It's a parched, desiccated environment. It's really hostile to life as we know it. There may be some life clinging on somewhere, maybe in the deep subsurface, but the surface of the planet is a dead world. And so this is in some sense a disappointing result, but it actually is a result. A claim was made earlier. The claim was that the surface of Mars is inhabited by a global biosphere in the same way that Earth was. And there were serious papers in the literature, in the peer-reviewed literature, which reported evidence of this. There were review papers written about the evidence for life on Mars. And with one stroke, with one image, Mariner completely falsified all of those. And so that's been one major output of the planetary exploration program. Okay, so the situation is bad for Mars. What about Venus? People played much the same game with Venus. Even 200-300 years ago, folks realized that Venus was closer to the sun than the Earth was, so it was likely to be hotter. And so folks even then knew that if you have a hot planet, that if on Earth you go to the hotter regions, they end up being a lot cloudier because of more water vapor evaporation. And so they looked at Venus, they saw that it was swathed in some kind of clouds or haze, and they argued that this was evidence that Venus was a swamp planet. So you had images like this being printed in not scientific journals, but popular science textbooks and things like that, arguing that if you could somehow get below the cloud layer on Venus, this is what you'd see. You'd see swamp world. There would be water everywhere, there'd be vegetation, it would be overgrown, it would be fecund with life. And here too, planetary exploration program put a kibosh on that. So this is an image from the Venera lander from the Russians. And it again reveals a world that's fascinating in so many ways. It has a really interesting distribution of hazes in its upper atmosphere, which seem to have really interesting chemistry. There's an unknown UV absorber there, whose composition we still haven't been able to deduce, and whose composition is contradictory in many ways. The data are not completely consistent. But one thing it doesn't reveal is any evidence of not just life, but habitable conditions. Again, totally parched, desiccated planet, no evidence of liquid water, and in fact, conditions hot enough to melt lead. So not the most appealing place. So after Mars and Venus, we've searched a bunch of places. We've looked in the subsurface of the icy moons of the outer solar system. We've started to scrutinize the hydrocarbon lakes of Titan. And we've identified a number of potentially habitable niches, places where life as we know it might potentially, if it tries really, really hard, just kind of barely eke out survival. But what we haven't found is any evidence of a global biosphere like we have here on Earth, a planet where life inhabits the entire surface the way it does here on Earth. And so that's a result that within our solar system, we are unique. Within our solar system, we are unique and quite possibly alone. And so that's one major thing that we learned from the initial age of planetary exploration, one thing those initial 40 years of missions taught us. And so once this became clear in the 1990s, once all the easy places to check had been checked and there was no evidence of space fish on Europa or what have you, the entire field focused on the search for life beyond Earth kind of fell into eclipse because we had checked all the places to check and there was really nothing. There really wasn't any good evidence. In fact, not only had we not found evidence to support life elsewhere, we'd found good evidence to say that life wasn't elsewhere. For example, there's chemical disequilibria in the atmosphere of Mars we've detected that life should be able to eat if it's there, but it doesn't. So that doesn't sound super great for Mars. And so the entire field kind of went into eclipse, and we were reoriented to focus more on astrophysics and planet formation and stuff like that. Things changed a little bit starting in 1995 with the discovery of so-called exoplanets, or planets orbiting other stars. And this, in a sense, was a really, really major revolution. And I apologize, it did this during the setup as well. Okay, cool. So this is just a graphic where I'm showing the discovery of exoplanets. So this is the sky. On the sky, on the top is year, and on this screen, you're going to see little dots appearing, which is where different exoplanets are being discovered as a function of time. So the first exoplanet discovered was 55 Cancri was 51 Pegasi b. There was a huge kerfuffle about whether or not it was real, but slowly, as more and more other exoplanets started to be found and multiple corroborative techniques started to come online, those question marks started going away. Initially, the field was dominated by ground-based searches, but it really exploded in the early 2010s with the launch of the so-called Kepler mission, whose effect you're about to see real soon, popping up right over there. Yep. And so to this day, most of the exoplanets that have been discovered by this Kepler mission, which was basically just a super high precision photometer lofted to stare at a patch of sky. This video is highly out of date. It ends in 2019 when we only had about 4,000 exoplanets, and now we have over 6,000 known. And so that is really kind of exciting. Prior to these missions, it was people were writing papers and actually books about a theory called rare Earth. The idea that life is intrinsically rare in the cosmos, and one of the reasons it's rare is that habitable planets themselves are intrinsically rare. Planet formation is just not very common. And the discovery of exoplanets falsified that pessimistic idea very spectacularly. So as I mentioned today, we know over 6,000 exoplanets. We've started to characterize them in their atmospheres in increasing detail. And this has given rise to the question, okay, there's all these planets out there. Are any of them like Earth? And are any of them inhabited? So it's kind of the age of exploration, the age of space exploration repeated. We've discovered that there's other worlds out there, and now we're asking what are they like and could they be inhabited? Here too, we've started to get some amount of information. So right now, it's been a struggle characterizing these objects because they're so far away. But some of the data we are able to get are their masses, radii, and their temperatures. And in particular, we can tell what they're made of. Are they rocky or are they gaseous? And roughly how hot are they? Do they orbit in the so-called habitable zone, in which they receive an amount of starlight that's compatible with surface liquid water? Or do they orbit interior to it, where they're like Venus, or exterior to it, where they're going to be like Mars? And so this is actually a question we've been able to answer is, what is the frequency of potentially habitable planets in the cosmos? This is work that's been done by a bunch of folks, but I argue with very little bias that the best work on this has been done by folks at LPL, led by Ilaria Pascucci. They combine data from a whole bunch of spacecraft, Kepler and TESS, but also the Gaia mission, as well as ground-based surveys and stuff like that. And they actually calculated the answer, which is roughly 10%. So and this is actually a really remarkable finding to come to. Sure, it's not 100%, that would have been super nice, but it is 10%. This means that if you take a group of 10 stars, one of them has a planet roughly the size of Earth, receiving roughly the same starlight as Earth does. And that's a really remarkable finding. That number could have been 1%. It could have been 1 in a million, but it isn't, it's 10%. And that means that there are billions of potentially habitable planets floating out there in our galaxy alone, and dozens within our solar neighborhood. And now we're in business, because if we expect to find dozens of these objects within our solar neighborhood, that is within the reach of near-term instrumentation. So this is a catalog of the rocky, likely temperate exoplanets that we know of. So you have the solar system planets over here. Just to give you a little bit of context, everything is to scale relative to Jupiter and the Earth. And the distances are listed over here. So the nearest one is Proxima Cen-b. We haven't gotten a lot of data on that, but we might get it soon. The UVA is developing new instrumentation designed to separate its starlight out directly. And the further out you go, the more of these objects you find. Once you're about 10, 15 light years away, once you're about 10 or 15 parsecs away, you have dozens of these objects, which is super fantastic. And so the field now confronts the reality that there are a ton of potentially habitable planets out there, and that might be inhabited. And this was a serious enough possibility that a little over a decade ago, about 2 decades ago, the Vatican decided it had to confront the possibility that we discover life elsewhere. And so they actually convened a major symposium. They got together a whole bunch of theologians as well as scientists to basically address the question, what happens if we discover life out there? What does it mean for religion? What does it mean for faith? And this was a huge deal. My old advisor participated in this. There was a whole bunch of stuff back and forth. Here too, there's very strong University of Arizona and State of Arizona involvement. One of the big folks involved in this was Brother Guy Consalmagno, who's an alumnus of the University of Arizona LPL. So, sorry, Stuart, he's one of ours. And he was one of the folks that was kind of mediating this discussion a little bit. And the overall conclusion that they came to is life can exist out there, and it's completely fine theologically. It's completely compatible with religion. And so there's not going to be another kind of like potential conflict like there potentially was a little bit with Galileo. The church is completely on board with this. There is no challenges for the search for life elsewhere. So we are clear to go, full steam ahead. Okay, so this is all well and good. We've discovered a number of potentially habitable planets out there. We've gotten the go-ahead from the elders that it's okay to go and check them out for evidence of life as we know it. But how the heck are we going to do this? These objects are not just millions, but hundreds of trillions of miles away. They're many light years away. There's no potential way to get a probe out there whatsoever. There's no way to ground truth it in the same way as we did with Mars and Venus. So how are we going to avoid fooling ourselves in the same way that we did with telescopic observations of those objects right here on Earth, right here in Arizona? Is it even remotely possible to remotely detect evidence of life on the planet? I will, in the remainder of this talk, make the case that the answer to this question is yes. Not only is it doable, it's doable with relatively near-term technology over the next 20 to 30 years. And I will attempt to make this case by presenting you past work done by Carl Sagan back in the 1990s, which validated this entire idea and gave us a sense that this is something we might conceivably be able to do. So this image over here is of the Galileo space probe. The Galileo space probe was a spacecraft that went to study the planet Jupiter and its moons. But Jupiter is pretty far away, so in order to get there, it had to do a flyby of Earth. And when it did, Carl Sagan somehow got together with his friends and convinced NASA to let them play Let's Pretend. Specifically, he got them to play Let's Pretend we are an alien civilization orbiting Proxima Centauri, and let's pretend that Galileo is our interstellar space probe that we've sent to this the third planet from this yellow star that's our next door neighbor. Based purely on evidence that you can collect from the Galileo space probe, plus the fundamental laws of physics, chemistry, and geology. Can you make an inference about the presence or absence of life on this object over here? And the answer they came to was a resounding, yeah, probably. So the strongest evidence that they found for the presence of life on Earth came from the so-called spectrum of the planet. And so when they measured a spectrum of the planet remotely from Galileo's instruments, they observed molecular features corresponding to a number of molecules whose presence was relatively hard to explain. So the weirdest stuff that they found there was a simultaneous presence of a lot of oxygen and methane. Those molecules were both present at such high concentrations that they should mutually react, they should burn at a relatively high cadence. The fact that they were both present in these concentrations, they used photochemical models to calculate the implied production rates and found that while abiotic mechanisms could explain one or the other, they couldn't explain the coterminous presence of both. That rate was just too high for the known processes that they were able to inventory. There was some corroborative evidence as well. For example, the presence of N2O, which there are abiotic ways to make N2O. The main one is lightning. But when they imaged Earth from Galileo, they did not see evidence of a global lightning storm. So that explanation didn't seem super plausible. So they concluded that N2O was corroborative evidence of life on Earth. And then they also noticed that there was H2O present, which combined with the presence of specular reflection on the surface of the planet, coupled with climate modeling, which indicated a relatively temperate surface environment, suggested that the planet was habitable, that it had surface liquid water. And so the inferential chain that they performed was, okay, the planet is rocky and temperate. The spectrum indicates oxygen and methane are present. They calculated how much, what the production rates of oxygen and methane had to be to explain the required observations. They compared that to known abiotic mechanisms and concluded that the known abiotic mechanisms did not explain the could not simultaneously explain the observed methane and oxygen fluxes. And they commented that the H2O suggested that the planet was habitable. This was so what they basically argued is we've ruled out the abiotic mechanisms. We've shown that biology is a reasonable explanation because it's habitable. Therefore, by principle of exclusion, Earth is probably inhabited. But again, they concluded in their paper they concluded that this was a conclusion they were reaching reluctantly, because whatever life was present on Earth had to be super weird, because life as we know it is based on organics, but the planet is oxygen rich. And how does that make any sense? The reason they made this statement is that prima facie, if you go talk to an organic chemist, they will tell you that it is the weirdest thing on Earth that life on Earth breathes oxygen. Oxygen is violently toxic to all organic molecules. It destroys them, it burns them. And one of the main ways it affects them is by the generation of so-called oxidizing free radicals. So oxygen-bearing molecules exposed to any kind of reactive power, whether that's UV light or particularly high-energy compounds, tend to give you these so-called free radical species over here, like peroxide and things like that. And those just love reacting with your biomolecules. They love reacting with your DNA and giving you cancer. They love cleaving your proteins, amino acids. They just love destroying everything. And in fact, to deal with this, life has developed a series of incredibly sophisticated detoxifying pathways that consume significant amounts of energy to keep us stable in the presence of oxygen. In fact, it's been proposed that the first mass extinction was the great oxygenation event, when oxygen first suffused the Earth's atmosphere. And there's some limited evidence for this from the phylogenetic record of organisms here on Earth. And so that's again, they're not letting themselves know about the nature of life on Earth, that we've evolved peroxide, dismutase, and all these other enzymes. They're just saying, based purely on the zeroth order principles of physics and chemistry, can we make an inference about the presence of life on Earth? And the biggest counter-argument to life on Earth that they came up with was the fact that it would imply that organics can coexist with abundant free oxygen, which prima facie is poisonous to organics. And so this was all well and good, and it's good for a chuckle, haha, the scientists only have a probabilistic constraint to the presence of life on Earth. But it is actually, in some sense, extremely realistic. It gives us, they really didn't cheat. They really didn't, to the best of their ability, they tried to be very self-skeptical about whether or not they could make this inference. And the fact that they were able to even place this probabilistic constraint is really promising. It gives us our so-called recipe for remote life detection. So our recipe is, we're going to start with the fundamentals, which is the observations. The fundamental observation is going to be measuring an atmospheric spectrum. That's the big goal. That's the thing we need above all else to characterize the atmosphere and look for sources of kinetic and thermal disequilibrium. And then we also need to measure the planetary and stellar bulk properties in order to get the context to figure out if the object is habitable. Once we have these data, we're going to comb through them to identify potentially biogenic gases that are generated by life and probably aren't generated by abiotic mechanisms. Even so, we're then going to once we've cataloged them, we're going to determine if the known abiotic mechanisms can explain the observation, can explain the presence of these molecules at the concentrations at which they're observed. If and only if the answer to that question is no, will we proceed to the biogenic possibility? Then we'll use our theories of habitability and inhabitability to assess the plausibility of a biological explanation. If and only if a biological explanation is plausible, will we conclude that we've placed a probabilistic constraint that life is probably there. Although we'll have to concede that we'll never know for certain until it's 500 years from now and Scotty takes us there. So, okay, this is all well and good. We have our recipe for remote life detection, but how are we actually going to implement it? Let's focus on the first part. which is getting the fundamental data, getting the fundamental measurements of the planet's atmosphere. We can't have our fight about the interpretation until we get the data first. So how do we go about characterizing the atmospheres of planets hundreds of trillions of miles away? These days, with the facilities we currently have available, we use a technique called transmission spectroscopy. So the short answer is we can't do it for most objects. We could only do it for a handful of objects which are fortuitous in the sense that from our point of view, they transit their star. From our point of view, they appear to pass in front of their planet's star. So it's a huge coincidence. A very small fraction of planets have this happen. But for the small fraction that do, something very special happens. When the planet passes in front of its star during the moment of so-called transit, some of that star's light passes through the planet's atmosphere. When it does so, that planet's atmosphere selectively absorbs some wavelength of that star's light, depending on what the composition of that planet's atmosphere is. If we measure the star-planet spectrum carefully enough, we can extract this and use that to place a constraint on the composition, the makeup of the planet's atmosphere. So today, we're only able to do this for gas giant planets. And we are able to make some detections. For example, we are able to robustly measure the presence of alkali metals in their upper atmospheres and their exospheres like sodium and potassium, as well as the presence of water vapor. Except I lied. This would have been true 3 years ago, but it is no longer true today. This is the way it was yesterday when we only had the Hubble Space Telescope to play with. But now we have the James Webb Space Telescope. And this, of course, blows that away. So this is this is the same planet, but the spectrum is no longer just the Hubble spectrum. The Hubble spectrum is still here, but it's just this part of the spectrum over here. And now you have this gorgeous high accuracy part of the spectrum out in the near infrared, where all the molecules are absorbing. And you're able to not only confirm those earlier detections, like the presence of water, but you're able to detect a whole fleet of other molecules as well, such as carbon dioxide, and perhaps most importantly, sulfur dioxide, which is evidence of photochemistry operating in a planet's atmosphere. And so this is a huge, huge deal. We are now with James Webb able to robustly characterize the atmospheres of gas giant exoplanets, which is amazing. And so this naturally begs the question, James Webb can, with just one observation, one relatively short observation, measure with exquisite precision the atmospheres of giant exoplanets. What can it potentially do for small exoplanets? And so what we'd really like to do is get a spectrum that identifies a potentially habitable world. So if you just take spectra of the small planets in our solar system, that would be Mars, Earth, and Venus, and you just stare at it, Earth just really stands out. Mars and Venus have basically the same spectrum in the infrared. It's CO2. That's really all there is. There's other things you can get if you go into a lot of depth, but to first order, their atmospheres are completely dominated by CO2. Earth, by contrast, has a much more complicated spectrum. It does have some CO2, but it also has water vapor, it has ozone, and a whole bunch of other goodies. So to first order, Earth looks different. The sole example of an inhabited planet we have in our solar system looks different compared to the uninhabited planets. And recognizing this opportunity, NASA has actually decided to move forward with building a telescope that can make that observation, that can image a solar system at a distance of 10 parsecs and differentiate Earth from an exo-Earth from an exo-Venus or an exo-Mars if they're present. So we have James Webb right now that's attempting to do this for a few fortuitous objects, primarily around low-mass M dwarfs, which I won't talk about right now. We're building ground-based telescopes that have the potential of doing so for a handful of objects. But what NASA really wants to build is this telescope called the Habitable Worlds Observatory that can do this for hopefully at least 25 objects and maybe even more. So this is just a quick video of what HWO is supposed to look like. It's supposed to be a mirror in the same size class as the James Webb Space Telescope, so 5 to 6 meter aperture. It's like the James Webb Space Telescope, it'll be substantially deployed in space. It needs a gigantic sunshade because not only does it need thermal stability, it really needs to block out all the spare sunlight. So like the big problem with these telescopes, with this problem, isn't getting the photons. Hubble detects enough photons to measure the spectrum of an exo-Earth. It's blocking out the contaminating starlight, first and foremost from our own sun, but also from the host star of that planet. And so to do that, that's what we need the coronagraph for, which is a really high precision piece of equipment that'll selectively block out the central light of the star. And let you image the planets around it. So this is a simulation of what HWO is, the Habitable Worlds Observatory is hoping to be able to detect. So this is a simulation of what the sun, our solar system would look like to HWO viewed from a distance of 10 parsecs, about 30 light years. And so you have the coronagraph over here blocking out the light of the sun. And then you have, of course, the big gas giants out here giving you really strong signals. But what we care about is digging into the noise over here and really going in depth over here and getting those few particles of light that we can get from Mars and Venus and ideally Earth. So this is what we want to do, and this is what we think we can actually do with near-term facilities. Lee Feinberg is actually coming and giving a colloquium here on Thursday. He's the chief technologist for this mission. And if you guys are interested in this, I'd highly encourage you to come and check out that colloquium. He'll be talking about the current state of technology and what they view the major barriers as being. But overall, the community does think this is doable. And so as a theorist, I'm sold, I'm happy, great, someone else is gonna handle this part, we're gonna get the data. So let's take the idea that we'll get the data for given, hand wave that away, it's engineering, who cares? And let's focus on what to me is the fun part, which is once you get these data, how are you gonna use them? How are you gonna execute this part of the life detection check, the recipe for life detection? So this is what I focus on, this is what I think is super exciting, and it's what I just feel really privileged to have the opportunity to spend some part of my day every day thinking about it. One of the gases that I really care about and I think a lot about is oxygen. The reason I think so hard about oxygen is that to first order, this is the single molecule that most strongly differentiates the inhabited world in our solar system from all the rest. Almost every other gas, methane, carbon dioxide, whatever, at least one of them you find on one of the other planets in our solar system, big or small. Oxygen you find nowhere else. So in some sense, oxygen is the canonical biosignature. It is the elephant in the room. It's the thing you have to address. So it might be that isn't to say that oxygen is perfect as a biosignature gas, and so once you get past the order zero, that on modern Earth today, oxygen is what you're going for. If you think harder about it, there's reasons to think that oxygen maybe isn't the greatest thing in the known universe. In particular, one of the major problems with oxygen is that oxygenic photosynthesis emerged relatively late. So here I'm showing you a graphic of basically the history of oxygen on Earth. The x-axis over here is time in billions of years ago. So this over here is modern day. This is about 4 billion years ago. The y-axis is the amount of oxygen in the atmosphere in log scale, normalized to what we have today. So up over here at 1 is modern levels of oxygen. And if you go back about 4 billion years, there was on the order of 1 million times less, at most 1 million times less oxygen. This is actually an upper limit. If you do model calculations, the models actually predicted that the oxygen concentrations were on the order of less than a part per quadrillion. So that is just an incredibly anoxic atmosphere. It's actually not possible to generate that anoxic an atmosphere here on Earth, which is a real problem for my experimental colleagues when we try to simulate that. We have continual oxygen leakage. It's a real challenge. But the main thing that I'd like you to notice over here is that the oxygen only starts appearing about 2.5 billion years ago. So for roughly half of Earth's lifetime, it had no oxygen. So if you assume a random sample of planets, even if you assume that you detect, let's say, 30 Earth-like planets, and all of them are not just habitable but are inhabited, you only expect about half of them to host detectable oxygen in their atmospheres. So that's one of the major challenges with oxygen. So that's one of the big negatives for oxygen. But let me tell you one of the big positives, which is that oxygenic photosynthesis is like an almost unbelievably, fantastically, thermodynamically favorable biochemical pathway that we think is very likely to emerge on diverse planets out there. And we expect it to emerge. On other planets out there because it is almost comically good. It is amazing in terms of the energy yields you can get and the substrates that it uses. Let me walk through briefly why it's so just amazingly good over here. So this is a schematic equation for oxygenic photosynthesis. What you basically have is you have carbon dioxide and you have water. They come together with sunlight as a source of energy, and you end up with fixed carbon, so carbon reduced into a hydrocarbon that can be used by biology, and oxygen, which is dumped out as a waste product. So why is this so comically good? Like, this is so comically good that if I was writing a science fiction book about it, I wouldn't put it in, because I would be like, this is just too unrealistically good. The reason that oxygen is so just incredibly good is the substrate, to first and foremost, is the substrates that it uses. It relies on carbon dioxide and water. Carbon dioxide is the most cosmically common form of carbon that's present on rocky planets. Pick volcanoes on Mars, on Venus, on Earth. Almost for any combination of melt parameters, carbon likes to come out as carbon dioxide and nothing else. So oxygenic photosynthesis utilizes the most abundant source of carbon that's available in planetary environments. The same is true with hydrogen and oxygen. Both of those molecules on a planetary context are most abundant in the form of water on the surface. No other molecule. So this is, again, the thing it uses something that's extremely cosmogenically common. And then if you look at Big Bang nucleosynthesis and as well as stellar nucleosynthesis, the molecules and atoms that are made by the universe and by stars, these are the atoms that are the most common. So like oxygenic photosynthesis is powerful because it exploits common, universally available reagents. It is in fact so common that it isn't. The other reagent that it employs, a source of free energy, is the sun. And this is, again, just incredibly common. Stars, if you're in a habitable planet, if water is liquid, you have to be orbiting a star relatively close, which means you have to be getting a free lunch in the form of photons. If you can figure out how to exploit that, boom, free energy source, really easy to get, amazing. This is in fact such an efficient photosynthetic path, energy yielding pathway, that if you quantify whether what fraction of the light that falls on the surface that biology actually uses, it's on the order of 1% or so. So we only use 1/100th or so of the energy that we could be using. And the reason we use so little is that life on Earth is not energy limited. It's not energy limited, it's not substrate limited, it's in fact micronutrient limited. We're limited by our supplies of fixed nitrogen and phosphorus, fertilizer basically. And that's an amazing, amazing regime to be in. That's just utterly insane. Once oxygen and photosynthesis was evolved, it was so efficient, so powerful, so productive, it just outcompeted everything else on the planet in a very short time. And so that's one of the reasons we think the big negative for oxygenic photosynthesis is that it's super complicated. It produces toxic oxygen. You have to evolve ways to deal with that, but it's worth doing it because it's such a powerful metabolic pathway once you get it. So that's one of the reasons we think it's it's likely to be universal. Okay, so far this is the positives for oxygen so far. One thing that scientists do whenever someone comes to a consensus is no one likes a consensus. Everyone wants to prove the big boys wrong. And so one thing people started saying was, okay, oxygen is looking pretty good. How do we bust it down? It can't be that good. There's got to be some weakness somewhere. And so far we've addressed the detectability question. Oxygen's pretty detectable. We've addressed how likely is it to evolve elsewhere. That seems pretty likely. But what about false positives? What about abiotic mechanisms that can generate abundant free oxygen? And so for the last, I would say since about 2002, people have been playing a game where they try to come up with theoretical ways to generate abundant free oxygen on a habitable planet environment. There's been like 30 or 40 papers on this going back and forth. But I'm here to tell you that all of those papers actually boil down to one of two basic fundamental mechanisms, either escape-based false positives or so-called photochemical false positives. The escape-based ones are perhaps easier to explain. They focus on the water vapor part of the oxygenic photosynthesis. So if you have a habitable planet, you have to have water vapor. Water vapor has a little bit of a problem. It's photochemically unstable. If you shine UV light on it, it really likes to break apart. When it breaks apart to ultimately give you molecular hydrogen and oxygen. The oxygen is fine, it can stick around. The hydrogen is super light. It tends to escape. And so this is a mechanism that can potentially give you a ton of oxygen buildup. Now it doesn't. It hasn't here on Earth. It didn't on Mars and didn't on Venus. And the main reason for that is reactions with the subsurface. So on Mars, for example, we do think this process happened, that there was a bunch of water on Mars. The water photolyzed and the hydrogen escaped. The oxygen remained behind. But we think we know what happened to that oxygen. It reacted with the surface. It literally rusted the planet. The planet is red because all the iron on it has been oxidized. And so that's a major sink. So if you want to get abundant abiotic buildup of oxygen on a rocky planet, you have to figure out some way to prevent the surface from reacting with it. That's if you read the caveats of all the escape-based false positive, that's one of the things they always say is you neglect reactions with interior reductants. I'll give them that. If you neglect reactions with interior reductants, it is possible for this to build up to large concentrations. I just don't think you can. And I don't think you can because of the example of Mars, which directly shows us from the red coloration and the chemical analyses of its surface that those interior reactions that do happen. And the same with Venus. We actually have measurements of the upper mantle state of Venus. It's much more oxidized than Earth this is. And and that appears to be evidence that the runaway hydrogen loss and oxygen buildup on Venus also ended up going into its interior. So this is one reason that I personally don't get as worked up about this class of false positive. A class of false positive I do get very worked up about, and consequently, which I spend a lot of time thinking about, are the photochemical false positives. The photochemical false positives comes if you focus on the carbon dioxide part of this equation of photosynthesis. So you have carbon dioxide over here. Turns out that carbon dioxide also is photolabile. If you shine UV light at shorter wavelengths, at about 200 nanometers and shorter, it photolyzes to carbon monoxide and atomic oxygen. The reverse reaction doesn't happen because of quantum mechanics. It turns out it's spin forbidden. So it doesn't just go into reverse. Instead, the oxygen atoms tend to react with each other to give you oxygen gas. And so this is another way of getting abundant free oxygen. And this is actually something that's validated within the solar system. Specifically in the atmospheres of Mars and Venus, there is small amounts of free oxygen present there. And it seems to be present due to this mechanism over here. So this is a basic universal problem that happens when you consider CO2-rich atmospheres. There is one fly in the ointment here, which is that while these planets do have small amounts of trace oxygen, Mars has about 10 parts per million, Venus has, I think, a little less than a part per million or so. You still don't have a lot of free oxygen. You still don't have on the order of 10% free oxygen, like we have here on Earth. And the good news is a Mars-like level of free oxygen would not be detectable, so that wouldn't be a false positive. But what if you could break this? So the lesson from the reason that happens on these planets is it turns out the small amount of free water vapor they do have. So earlier I described that the CO2 tends to fall apart to CO and O2, but those atmospheres don't just contain CO2, they also contain tiny amounts of H2O. And these amounts of H2O are really, really tiny, but they're not zero. And they can participate in what are so-called catalytic cycles. So H2O can photolize to give you H and OH. That OH can react with the CO, it can react it back to CO2, and it can trigger a catalytic cycle whose net effect is to combine the CO and O back to CO2. And so the lesson from the solar system is that trace amounts of H2O plus the UV light required to photolize it can stabilize CO2 and prevent it from accumulating a whole bunch of oxygen. And so naturally, what scientists automatically turn to is ways to break this, ways to break the stabilizing loop. And so there have been a whole bunch of ways that have been thought about over time. One argument is, what if you have a planet that just doesn't have any hydrogen on it, that just doesn't have any catalysts? And to be frank, that probably does hold up. If you have a planet that literally has no water on it, no methane, no nothing, no source of hydrogen atoms, you're probably going to get a ton of abiotic oxygen buildup. The good news is you can detect if that scenario is operating because there won't be any hydrogen-bearing molecules there. If you detect literally any hydrogen-bearing molecule in the atom, whether a molecule in that atmosphere, whether it's water vapor, whether it's methane, whether it's any of that stuff, then you can confirm that this mechanism is not operating. So this is a concern, but it's one that can be mitigated by designing your telescopes to look for not just oxygen, but also other gases as well, most importantly, water vapor. There was another false positive that was suggested. It turns out that volcanoes, if you look at the details of these mechanisms, are important for stabilizing carbon dioxide. And it was proposed that maybe you have planets which just have very low rates of volcanic outgassing. And if that's the case, maybe you get a bunch of abiotic oxygen building up. There was actually a huge debate on this for about 2 decades or so, with different families of models disagreeing. And one of the big things that I've been doing over the last few years is leading modeling comparisons that figure out why those models are disagreeing. And it turns out that the main reason that these models were disagreeing was different assumptions regarding the absorption properties of some of their chemical parameters, most significantly the absorption properties of water vapor. We went out and measured them. And we showed that if you use the correct properties, this false positive goes away. So this false positive for oxygen as a biosignature now stands refuted as well. The final, so both of these false positives were basically about getting rid of water in one way or the other. The other thing you can try to do is get rid of UV light. It turns out that there are some stars which just emit very little UV. And so it was argued that the planets orbiting those stars are systematically vulnerable to build up of abundant free oxygen. I led a model into comparison which ended up showing that that too was purely a model artifact, and that this false positive also does not hold up. And so overall, my takeaway is that oxygen is not a bad biosignature. It's actually a pretty good one. There's only one known photochemical false positive, and it's relatively easy to discriminate and identify spectroscopically. So, so that's been kind of my core work over the past decade or so. But this may not be satisfying to you. You may be saying, well, this is all well and good, but it's really model dependent. You still need to detect oxygen. What if you're one of those planets that just never evolved oxygenic photosynthesis to begin with? What then? Well, the nice thing about this whole approach is that the fundamental observable we're getting is a spectrum. And you can design this spectrum to look for oxygen and methane and things like that. But a spectrum will detect any gas that's present. It's like as long as it's absorbing within that waveband, we can detect it. And so that means that you can look for other indicators of life as well. So people have looked at a whole bunch of different potential indicators of life as we know it that are not as closely motivated by modern Earth as modern Earth. I won't go into that right now. You can ask me about that in the Q&A if you like. But one thing that frustrates people about those, as well as each of them have their false positives as well, and that's led to people asking, is it possible to, what could you look for that doesn't have any known false positives? The only thing we've been able to come up that has literally no false positives are so-called technosignatures. In other words, evidence of not just life, but a technological civilization being present. So if planets were inhabited by a tool-using species that develop technology, you can look for that as well. Some of the things you can look for is you can look for evidence of pollution. So if for example, there's species on Proxima Centauri b that are polluting their atmospheres with CFCs the way we were doing back in the 1960s and 1970s. Maybe not the greatest thing in the universe for them, but super great for us because CFCs are extremely detectable. They have really strong spectral features. And there's been work done which shows that that various kinds of pollutants that our civilization has made at one point or another in its history, if another civilization was making them at comparable rates, the same instrument that we're designing to look for basically algae, designing to look for oxygen and methane and things like that, would be able to pick up on that as well. Similarly, it turns out that the kind of artificial lighting we use imprints a strong spectral signature as well. We can look for that as well. And of course, we can also look in the radio for evidence of radio transmissions, just directly SETI. But what happens if we look for all of that and we turn up a blank? What happens if if the same thing that happened in the solar system happens for exoplanet systems as well? We go out, we look, and we find nothing. In fact, we place strong upper limits. We show that global biospheres on these objects cannot be common. Have we spent $10 billion building this telescope for absolutely no science return? I argue that's not the case because this is a problem for which even non-detections are informative. Specifically, for the since the Miller-Urey experiment and in the 1950s, people have been trying to figure out why the heck we exist. Why the heck is there life on Earth? And we haven't been able to answer that question to anyone's satisfaction yet. That's still a major unknown out there. One explanation that's been put forward is that maybe people have come up with different ways, some ways that life can be formed, but they require extremely specific conditions. So no one's really satisfied with those particular mechanisms because they're like, well, that requires a lot of fine tuning. That can't be how it happened. That's again the principle of mediocrity in action. We're assuming that we're not special. It is possible that we're just special, that on our particular planet and no others, molecules happen to come together in just the right way to give rise to life. If we survey our local stellar neighborhood, going out to like 40 or 50 parsecs, we detect habitable planets, but we constrain that there's no life on them. All of a sudden, that particular explanation starts looking somewhat promising. And so this is a way in which, even if you have non-detections, it still tells you something basic about the rules of life in the cosmos. Another way in which Habitable Worlds Observatory could tell us a lot about life, even without detecting any life out there, is it could give us a window onto early Earth. So again, one of the big questions people are trying to figure out is how the heck life evolved here on Earth. One of the barriers that you come up with doing that, with trying to simulate the origin of life in the lab, is that people can't really agree on what early Earth was like. They can't really agree what you should be simulating in the lab. And the reason you can't do that is because, ironically, because Earth is a habitable planet. We have a plate tectonics, which stabilizes our climate on long time scales, and we have free liquid water. And that free liquid water tends to erode rocks away. So the only rock record we have from billions of years ago comes in the forms of these so-called zircons, which are, the scale bar here is 100 microns. So like about the 100th of a centimeter in size. And those are the grains we have to gain some insight into what early Earth conditions were like. These really, really tiny, tiny, not even rocks, but flecks of rock that are preserved. And so this really limits our ability to try to simulate the origin of life in the laboratory. One thing that you could hope to do if you detect habitable but uninhabited planets is gain a window into what one of those looks like, and you could gain a window into what early Earth is like. And so people have started coming up with all sorts of predictions for the different species that would constitute the atmosphere of prebiotic Earth. And you could test those predictions, potentially with the Habitable Worlds Observatory. So even if you don't detect a biosignature with HWO, it could still completely revolutionize our understanding of life in the cosmos. So I'd like to close this talk with a summary. One thing that we have definitively learned is that temperate rocky planets orbiting other stars are common. And within the next couple of decades, assuming NASA continues to exist, we will measure the atmospheric spectra. The reason we want to do this is we want to search these worlds for evidence of life by looking for planetary scale biogenic modification, especially of their atmospheres, as has happened here on Earth. And to succeed in the search, we have to understand what are the potential biosignatures of life that we can look for and what their false positives are. Even if this search fails, even if we don't find life elsewhere, in another sense, we haven't failed, because that itself will be strongly constraining. Non-detections of biology will tell us that life is rare, that it is a fluke, and that it'll reinforce more than ever that what we have here in this pale blue dot is especially precious. I'd like to leave you with a surprisingly poetic quote from the last decadal survey. So about every 10 years, the astronomy community gets together and tries to summarize the progress in the last decade and what the priorities for the next decade should be. Normally, these are extremely tedious documents, hundreds of pages long, whose theses tend to be extremely technical descriptions of trade-offs and things like that. But the last decadal survey, the one that recommended the Habitable Worlds Observatory, had this really quite poetic conclusion when it recommended HWO as the highest priority NASA mission for the next couple of decades. Life on Earth may be the result of a common process, or it may require such an unusual set of circumstances that we are the only living beings within our part of the galaxy or even the universe. Either answer is profound. In the coming decades, we'll set the humanity down the path to determine whether or not we are alone. And so I'm super excited to be participating in that, as are you guys, through your support as US taxpayers. So thank you so much for that, and thank you for your time.
That is a lot to digest. Very exciting. So I can't wait for those observations. We've now got groundwork.
2045.
Ooh, long wait for me. He's going to have the thrill of his life when it happens. Questions in the audience. I see one here. Do we have some runners? Looks like you, Doug.
Two questions for you. One is, how has the advent of newer heavy lift vehicles shaped the design of the evolution of design of the Habitable Worlds Telescope in terms of, more mass to orbit and those sorts of factors?
That's a great question, and the short answer is not at all yet. NASA is an incredibly conservative organization, and until the technology exists, they're not allowed to assume that they'll have it. So if, for example, SpaceX's Starship comes online, everything will change. If Starship comes online, we'll be able to build and launch bigger mirrors than we can right now. So that would really profoundly change the equations for HWO. It would give you a much higher sensitivity and much broader reach, and it would frankly make the mission a lot stronger. There's even a more fundamental change that several of us would like to see happen, particularly here at the University of Arizona, which is the move to not just single large observatories, single spacecraft observatories, but fleets of smaller observatories that can work together in a modular way to do better observations. For example, Daniel Pai is working on one low-cost mission architecture. This works really well in a bunch of ways. Like, it's how industry does things. Historically, it's not how NASA does things. The basic trade-off you have is you launch, a constellation of 10 or 100 objects, and you have some failure rate, like you tolerate like a 30% or a 40% failure rate, and the rest. But like, it's fine because you over-design it so that it costs less in total because you don't have to do as much testing and validation, and the 70 to 60% you have left is enough. The problem is NASA is a national space agency. If any of NASA's spacecrafts fail, that's taken as a slight to US honor. The Chinese can point at us and laugh. So NASA is not allowed to have things that do that architecture just yet. So that's something that a cultural change that we have to implement if we want to get solutions like that working, new space solutions like that working.
The second question is, a lot of your work is focusing around Earth-like chemistries, specifically with oxygen, but you're not, granted you can't really prove this either way, is you have non-oxygen based chemistries or, different chemical compositions of planets that would mask some of the signatures that you're saying, hey, we should look for these.
That's a great question. I appear to have deleted the backup slide that discussed that, so I apologize for that. The short answer is that there's a profound cultural difference between physicists and there's differences in scientific culture with physicists on one end and biologists on the other. Physicists have a relatively universal perspective, or universalist perspective. The perspective there is that we're just one instantiation of a vast realm of possibilities. How do you know that we're special? You should really be designing things to look in a more broad way. And so if you approach it from a physics perspective, you can come up with a much broader list of biosignature gases to go look for. And so I was trained as a physicist. That's kind of the angle I come at from my perspective as well. And so I've participated in projects that have tried to articulate alternative biosignature gases, both based on gases that are produced by life on Earth, but not at very high rates, and asking in which situations might life produce a lot more of those, as well as in other situations, considering hypothetical biochemistries that aren't on Earth at all, but might evolve in other environments, for example, hyper-reducing environments like we don't have them. The problem is I can come up with those, and they might convince other physicists, but they won't convince the vast majority of the scientific community. They won't convince the geologists. Like, if you talk to a biologist, the biologists I've talked to, forget non-Earth-like biosignatures. A lot of biologists I talk to don't even believe in remote detection of spectroscopic species. Like the space telescopes that are the satellites that are monitoring atmospheric composition down here on Earth, they don't feel comfortable with that either. Their standard of proof is I need to be able to measure it in my own laboratory before I really believe it's there. Everything until I have it in my personal lab is provisional. And so those folks are never, ever, ever going to be convinced by non-Earth-like biosignatures. So if you want something that's going to give you some consensus in the scientific community, you're limited to Earth-like life.
You're in the
Wow, very nice talk. Okay, so we know from the Miller-Urey experiments that you can take a water and gas environment and you can have many different types of energy put into it, and the end product is organic goop that can evolve. Oh, why are you shaking your hand there?
It doesn't. We actually tried that. So I'll finish your question, then I'll give the overview on Miller-Urey and how it failed. Sure.
My question is to extend this. What if you have an environment like you have on Titan, where you have ammonium and other other gases there? Has anyone ever done the equivalent of a Miller-Urey experiment for a Titan-like atmosphere, and do you get organics out at the end? And that can be extended even to an environment much like what you have on Io, where you also have liquids there of different composition. You have sulfur compounds. And have people performed Miller-Urey experiments to find out whether in an IO like sulfur, I'm not sure what's there, you can get out what we would call organics at the end?
Those are great questions. I'm going to answer them in reverse order, starting with Io, moving on to Titan, and then concluding with Miller-Urey and its pros and cons. For Io, you don't actually have to resort to Miller-Urey type syntheses. And in fact, you can't. Miller-Urey assumes you have a significant inventory of gas. Io, the atmosphere is ultra thin. It's on the order of a microbar or so. So you just don't have the mass required or the carbon required to make organics. You can, however, you do, however, make stuff. Specifically, you make a lot of long chain sulfur compounds, most particularly elemental sulfur. That's been observed. And we can now actually model that formation in computer models. So we can explain Io relatively well. Titan we cannot explain super well. But people have, at least theoretically, but experimentally we can. People have done Titan analog mixtures in the lab, and they've simulated it to Titan-like irradiation conditions, proton bombardment conditions, and things like that. And they've reproduced observables from Titan as well. So that kind of synthesis does work for Titan. It's really easy to make organics. And that, in fact, is the problem, which is that, so let me go back to the first point you made, which is about the Miller-Urey experiment. Let me briefly recap what the Miller-Urey experiment is, what it found, and then the subsequent limitation that was found with Miller-Urey. Miller-Urey was an experiment done in the 1950s by a grad student named Stanley Miller, who was really sick and tired of his PhD program and wanted to just do something wild and wacky. And what he ended up doing is he went to a guy named Urey, who had come up with the theory of what early Earth was like. He's a fairly famous guy, Nobel Prize winner at the time. And he said, you know, you have this theory of what early Earth was like. Let me just, life emerged in early Earth. Why don't we simulate early Earth in a lab and see if life comes out? And Urey was like, you should not do this. The experiment will fail. You will not have a job. You will be homeless. This will be bad. And this guy, Miller, was just like, I'm super bored. I've tried doing Big Bang nuclear synthesis for like 2 years. It did not work out. I am sick and tired. I just want to do this for my last hurrah, and then I'll move, and then like, I don't know, I'll go and find another job doing something else. And Urey was like, all right, your funeral, you go for it. So that's what Miller did. He set up this little apparatus where he had water to simulate the ocean, a mixture of reducing gases to simulate what they thought the early atmosphere was like, and a spark discharge tube to simulate lightning. And he set it up and he let it run for a few weeks, and he came back and he measured what was inside. And he got super excited because what he measured was amino acids in relatively high yield. And amino acids are the building blocks of proteins, which are one of the most important kinds of biological molecule we have today. And so this gave rise to a picture that was really appealing to physicists like me, which is that the origins of life problem isn't actually a problem. All you need is the basic molecular atomic building blocks and a source of free energy and time. And you just let it run long enough and voila, it turns out that biomolecules pop out. And if biomolecules pop out in a couple weeks, give it a couple 100 million years, surely you'll get more you'll just end up popping out life whole formed. And so this was super exciting, and it was a really attractive idea, and many textbooks were written stating that the origin of life problem was solved. And people were like, oh yes, this sounds like it's going to work. Let's just do a couple of follow-up experiments to confirm that it's going to work. And the follow-up experiments they basically did is Miller-Urey was first immediately replicated by a bunch of different folks. They confirmed that you get amino acids over a broad range of conditions. They confirmed it's not sensitive to the particular mix of gases or the energy source. Wow, if you have free energy in the atoms, you seem to get amino acids. That just seems to work. So that part of it was confirmed. The next prediction the theory made is that this process should also eventually, if you give it enough time, it should be able to give rise to proteins. The amino acids should be able to link together to make proteins. You should also be able to make things like sugars, and you should also be able to make things like nucleic acids. And so people did a whole bunch of work to try to figure out, and they to try to make those. And they spent decades. They spent decades on it. First 1 decade, then 2 decades, and 3 decades, and all of those efforts failed. And then they started saying, well, maybe you really do need millions of years. Let's just measure the rate. If we can constrain we'll build really sensitive apparatus, so even if it's proceeding at a rate of 1 per million years, we can detect it at low yield. And they ended up placing extremely high limits that showed that it was occurring at a rate of less than 1 per every billion years or less. And so all of a sudden, like one of the things that the long and short of it is that we've learned that merely Urey type apparatus can give us amino acids, but they can't give us anything more complex. And it turns out there are fundamental chemical reasons for this that I can go into if you're interested. But yeah, there's basic chemical reasons that non-directed familiar Urey syntheses cannot give you oligomers and they cannot give you nucleic acids. That's where it fails.
We got one down here in front.
So we have to care about the chemistry. This is very sad for physicists like me.
I'm kind of reading into what you were saying, but my understanding is that if photosynthesis doesn't appear, the habitable planets, if there's life but non-photosynthetic life, you wouldn't be able to detect it. Is that right?
No, I'm being really conservative here. Sorry, I'm trying to find I have to page through a whole bunch of these. Okay, gosh darn it. Okay, so not necessarily. Photosynthetic life would be the nicest because that would have the least ambiguity. Like if you detected O2, if you detect an Earth twin, that's what people are going to fight with you the least about. You've detected a habitable planet. Because if it's literally an Earth twin, it has like O2, CH4, H2O, that kind of stuff, people are going to fight with you much less. There are still things out there that I, as a planetary scientist, would be convinced are inhabited, even if even in the absence of O2. For me, the most important molecule there is abundant methane, not small amounts of methane, but really gigantic quantities of methane. If you look at over Earth time, oops, is this not? It's not showing anymore. That's sad. Gosh darn.
Go ahead and reshare it, Sukrit. I had stopped it so we could see you guys better.
Oh, sorry. Okay. Yeah. Okay. I'm really sorry about that. Yeah. So this plot over here is showing as time on the x-axis, present day, about 3 billion years ago. Over here on the y-axis, it's a qualitative measure of detectability. On Earth today, oxygen is super detectable. If you go back about 2 billion years ago, there was no oxygen, but what there was a titanic amount of methane. And we actually have geological evidence for that. It's not just a model calculation. There's evidence from so-called xenon isotopes that there was a methane-rich early atmospheric state. There's abiotic ways to make methane, but there's not abiotic ways to make, we don't know of abiotic ways to make a ton of methane. We figured out abiotic ways to make on the order of 1 to 10 parts per million methane, but not to make percent levels of methane. So if you detect really abundant amounts of methane, which is from methanogenesis, which is an ancient metabolism, it emerged at least 3.5 billion years ago, to me, that would be pretty convincing. But the further you get from modern Earth, the increasing amount of doubt you're gonna get.
Okay, I actually have a couple of questions. While you're saying that, okay, Earth is unique in the solar system, it's the only one that's got life and so forth on it. That may not have been true earlier in the history. There's abundant evidence that at least Mars may have had life in the past, and perhaps even Venus may have started out very similar to Earth. Excuse me. First question, how does that affect your search strategy? Because can you detect planets in that early stage of evolution?
That's a great question. And let me just, I'm trying to find the plot that addresses that to some degree. Yeah, so the short answer is yes, we think so. So one of the things we try to do, one of the things we're working on now for the Habitable Worlds target star list, we know the stars we can image, and we're trying to do things like figure out their ages and things like that. And based on the knowledge we've built up over the last century of studying stars astronomically and developing models of their evolution, we're trying to figure out how do their habitable zones move over time. And so we're trying to account for planetary evolution in these processes as well. This is one of the motivations for being particularly interested in studying, excuse me, please, relatively young objects at a diversity of ages. We're hoping that even if there's no life, maybe we can get better understanding of how temperate terrestrial planets evolve and bifurcate in their evolutionary histories over time.
But wouldn't you have to look for different signatures to detect a planet like that?
To first order, we don't think it would be that different. So if it's habitable, right? Like if it's habitable, it's going to have a CO2 N2 atmosphere and it's going to have water on the surface. If that's true, how different can you get in terms of biosignatures? Like we only know of one kind of life that can exploit that environment, and it's organic stuff.
Okay, but like in the early Earth,
Mm-hmm.
you had almost no oxygen. So
Yeah.
oxygen would not, if you found a planet like that that didn't have much oxygen, how would you know that it would be a habitable planet if it's in that early stage of evolution?
Oh, we wouldn't. Yeah. So our current strategy accepts a high false negative rate. So we would the strategy that the National Academies has endorsed accepts that it's very possible that we're throwing away that our search strategy is throwing away a bunch of inhabited objects, and it does that in order to reduce the false positive rate. Yeah, that's a conscious choice that was made.
Okay, I have a question now. On the graph that showed the oxygen level in the Earth's atmosphere, what happened at 2.5 that it suddenly shot up?
Yeah, this is a somewhat major. Sorry, I don't understand why this is. Okay,
There.
yeah. This is I wouldn't say $1 billion question, but I'd call it maybe a $50 million question. There's entire subfields. Like this is a major question in paleogeology, is figuring out what the heck caused a great oxygenation event. There are two broad answers that have been proposed. One is geological, one is biological. Let me acknowledge my biases here. I think the biological answer is correct and the geological answer is wrong, but I will attempt to present both of them. The geological answer is there was a change in the redox state of the planet. So people argue that the mix of gases that was emitted to the atmosphere by volcanoes underwent a systematic change roughly at this point in time. Maybe because of the change in the continent mass fraction, maybe because of a geochemical change in the planet's mantle, something like that. You had a more oxidizing mix of gases that started to get put out at this point in time, which permitted oxygen to build up in the atmosphere. That's a geological explanation. If you look at that explanation quantitatively, I don't think it holds up, but we can have a debate about that. There's also a biological explanation, which I personally find to be a little bit more compelling. The biological explanation holds that what fundamentally happened is that oxygenic photosynthesis evolved, and it overwhelmed the surface sinks. So there's actually now evidence that oxygenic photosynthesis evolved relatively early in Earth's history, about almost even 3.5 billion years ago. But it was confined to a few local oases for a very long time, probably because outside of those oases, it had to figure out how to deal with all the oxygen toxicity. Once it exceeded those oases, it started producing a bunch, but it still didn't accumulate in the atmosphere. Because it was being emitted into the oceans. The oceans were rich in reductants like ferrous iron and sulfide, and it had to reduce all of those first. So that's proposed as the origin of the so-called banded iron formations. And once it reduced all of those, then it had to go into the atmosphere and reduce all the reductants that were there as well. And only by the time it reduced all of those could it then start building up in the atmosphere. But by that time, you had a ton of oxygen producers. So once you run out the sinks, you run up the concentration real fast. That's the argument that I tend to buy.
Okay, and then it starts to go back down.
Ah,
and then it
yes, the
comes back
overshoot.
up.
No one knows
Yeah,
that.
No one knows that. Okay.
Yeah, big fight. No one knows.
Okay, thanks.
And absolutely no one can explain this thing over here, which is a second great oxidation event.
Where in that diagram is the snowball Earth happening?
The snowball Earths that we have evidence for are happening around here. Sorry, they're happening between 0.5 and I think it's either 0.5 to 1 or 0.5 to 1.5 billion years ago. I don't remember the exact number, I apologize. But relatively geologically recently.
No YouTube questions.
No YouTube questions.
We
Any
can go to
questions
Zoom.
on Zoom?
I do have some on Zoom. Matthew Oda asks, is free oxygen the best biomarker for life on exoplanets?
That's a great question, and I think the short answer is it's the one that the most number of people would accept.
Okay.
So from that perspective, I think it's the one we have to design our instruments for, because it's what'll get consensus from the scientific community.
All right. And Jeffrey Johnston says, I'm curious about theories of life potentially being seeded on Earth. Is there any life known on Earth that, if subject to the harsh conditions in space, vacuum, intense radiation, cold, lack of sunlight, etc., could exist for potentially millions of years, survive entry into Earth's atmosphere, and evolve to create higher forms of life?
That's a great question, and the short answer is we cannot exclude that possibility. The major challenge here, we've confirmed that there exist spores of organisms that can survive those conditions. The major question is, can they survive those conditions for millions of years? And we're not able to answer that question because we have not yet existed for millions of years as a species. So we have not been able to do the experiment. People have tried to extrapolate a little bit by doing them under more extreme conditions and quantifying, okay, 0.001% of them were lost over a time scale of a month or so. So let's extrapolate that to a million years. You can play that game, but the problem is the error bars you end up with are absolutely ginormous because you're doing an extrapolation from like a time scale of months to a time scale of millions of years. So that's the major issue. Like what we normally say is we cannot exclude that possibility, but neither do we have evidence to support that possibility. This is one of the reasons, by the way, that I think that the search for life on exoplanets is the best opportunity to test theories for the origin of life. Because within the solar system, you have the risk of panspermic contamination, but that does not apply for exoplanets. The cross sections of collision are just too low.
All right, good. And then Gary Wells asks, is the Nancy Grace Roman telescope going to be a substantial contributor to the kind of data you will work with?
Unfortunately not. The Roman Space Telescope is going to do absolutely amazing things, both in terms of fundamental science. It's going to revolutionize our understanding of exoplanet demographics. It's going to do amazing things for our understanding of gas giants, and it's going to really help technological development for the Habitable Worlds Observatory. But my understanding is that its coronagraph is only really suitable for Jupiter-like planets, big planets far away from their stars. It is not going to be able to have the sensitivity to do Earth twins, small planets close to their stars. So it's a really important stepping stone towards HWO, and it'll do really important science in its own right, but it will not be able to do anything for this particular science case.
Okay, and final question is from Stephen Ferris. How do you account for the amount of methane in the atmosphere of Titan?
This is also a great question. I just had a paper on this come out last month. The short answer is that there's strong evidence that the methane in Titan's atmosphere is outgassed. So it's not generated there in situ, it's released from the interior of the planet. You see that from outgassing traces like argon isotopes and things like that. If you evaluate the lifetime of the photochemical lifetime of the current methane inventory in Titan, you find that it's geologically short, on the order of 20 million years or so. And so the typical inference is that the methane-rich state of Titan's atmosphere is a geological accident. We happen to get lucky. We're to exist during an era where Titan has a methane-rich atmosphere. It's after a methane outgassing event. But if we wait 100 million years or so, Titan might look a heck of a lot more like Pluto with a thin N2-dominated atmosphere with no CH4. Conversely, if we wait 100 million years, maybe Pluto will have a methane release event and it'll have a Titan-like atmosphere.
All right, thanks. And that's everything on Zoom.
Okay, we've got one more in the room here.
So in the terms of stellar evolution, it's known that stars generally form inside of some sort of stellar nursery where there's a lot more dense material, closer to nearby stars, other sorts of factors that, would allow material to potentially be exchanged between these systems. And you have just a lot more dynamic of an environment. So what, besides the fact that it might be a little bit more difficult, would be the main thing for preventing us from searching more in these younger open clusters that maybe have just diffused from their parent stellar nebula?
That's a great question, and the answer is they're just too far away. Our search volume with the technology we have access to, with the things that we can envision over the next couple of decades, is limited to If we get super lucky, like 20 or 30 parsecs, the nearest open clusters are, I think, like 1,000 light years away or something like that. So I think that's the main limitation. It's just too far away. We're limited to our boring solar neighborhood, just the right next door. That's what we can do.
Oh, we have another question in the back.
Go back to that slide with the poetry, and could you leave that up there? It's very
Uh,
beautiful. Thank you. The last one.
Yeah, the one
Poetic.
from the bureaucrats.
Thank you for your talk.
What was the question?
Was there a
sorry?
question?
Comment, if you want to look at life outside of, look at tardigrades. They live over 100 years. You know about that. They've been in outer space and back. You can't kill them. Seriously. And they even had tardigrades and went outside the space shuttle and laid eggs. Came back.
Yep,
I
they
mean,
came back.
yeah.
I think water bears have done similar stuff. Yeah, over a time scale of like decades, I think it's clear that they can survive.
Right.
It's just
Then there's-
extrapolating beyond that.
Regarding biologically, something called the age of gigantism in terms of more oxygen to relation to concentration of nitrogen, and that affected life on Earth as well. So that's why you had dragonflies like this and so forth. But
Yeah, there's a lot of interesting work being done on that. Earth's been so many different
this
planets
is
throughout
all
its
on Earth.
history.
It's not exoplanet.
Yeah.
Jim Hunter
Okay.
on Zoom also mentioned you should also use a quote from Will Rogers about life in the universe.
What is the quote?
I don't know. Tim, do you know what the quote is? You can unmute and tell us.
Yes, Will Rogers has a quote, something to the effect that life is either very common in the universe or we're all alone. Either way, it's a very sobering thought.
It sounds like the National Academies plagiarized him.
They did. He did that about almost 100 years ago. I don't know, you'd have to look at it, but I think that quote is fantastic.
Thanks, Tim.
I also have a question to follow up. If there's methane outgassing, where'd the methane come from and how did it get produced?
Oh, that we think we know. It's primordial. So in the disk, the thermodynamic conditions are such that carbon likes to be present in the form of methane. And you have direct observational evidence for this in the form of comets. So comets we think are relics of the early solar system. And when comets outgas carbon, they predominantly outgas carbon in the form of methane. So the typical argument is that the methane on Titan, like basically the idea is that Titan formed as basically a giant smushed up ball of comet stuff. And so that's where the methane came from. It was incorporated into the ice matrix. It's held there by the fact that it's super cold and the ice is basically a rock that acts as a mantle and seals it inside. And occasionally you have some kind of like major geological event that ruptures that ice crust and lets the methane that's inside outgas. So it's all, what's called natal. It was imprinted at the time of formation.
Sukrit, do you buy that?
I think so. But I also don't really know much about planet formation. You have to talk to Ilaria about that. I just read the thing and I'm like, oh, that sounds right. They seem to be doing a lot of math. Hopefully it's right.
Okay. With that, let us say thanks to Sukrit for bringing us a really stimulating topic. Thank you so much. That was a lively discussion on a subject. We hope we get some data you can analyze and come back and talk to us.
Thank you so much for having me.
Yeah, some of us will be there listening carefully. Thank you. Can you help me get on those slides? Well, I'm gonna bring you back to Earth. We've started a project 2 years ago that I want to review with you and bring you up to date with what's going on from just this past week. Our 32-inch gift that came to us in June of 23. It seems like just yesterday to many of us that went to pick it up. It's on the screen. Well, it's up there. You're sharing it. What do you
We're
have?
not seeing it. We're not seeing it on Zoom yet. Now we have it.
You see that, Jim?
Yeah, just go to full screen or go to presenter mode.
Down here. Okay, well, you got it. And now how will I change it? Okay, we'll just, okay. Okay. Okay, let's do that. Many of you will remember this picture from 2 years ago. This telescope, a 32-inch DFM research grade telescope, was donated to TAAA. The only problem was we had to go get it, and it weighed 2 tons. But we had volunteers make that happen. Not only going up there to disassemble it, but to haul it back. And one of our members, Warren Hensey, agreed to store it while we built a home for it. Next. Next. I know. Terry is our expert. Okay. There it is. It sat for 2 years, tucked away in Warren's location there in Cochise County. Next. And look at all those parts, 2 tons of parts. Until we built the observatory. The observatory took us a couple of years to both design and to build. And there you have it. It was finished this past June, 2 years after we got the telescope. Next. And this week, we have started to bring it to life. I have learned what a challenge a telescope of this size is. You know, when you're balancing your C11, that's pretty big and you got to be careful. When it weighs 2 tons, you got to be really careful. And fortunately, we have 3 of the people in that picture are engineers. And we are blessed with many engineers in TAAA and many wonderful volunteers. Let's look at the next one. Those volunteers have been under the direction of a very special volunteer, but you can see all the pieces coming together. It almost looks like a telescope here. Next. And there's a picture that really looks like we've got a telescope we might be able to point at the sky this week. I want to call out one person in this picture, though, the guy on the far right. He is not a member, but he is a very special character that we could not have done this without. Tom Melsheimer is a volunteer who has volunteered his time and his expertise to come and put this together. Many of you may know that DFM, the manufacturer of this telescope, that stands for Dr. Frank Melsheimer. That's Tom's brother. Tom has put together 80 of these. He's been all over the world to universities and major observatories installing DFM telescopes. When we were in Colorado and talked to Tom about TAAA and what we do, and started to tell him about what we do in terms of outreach, he said, I've got to show you something. And he took us to the local high school there in Colorado and showed us the observatory that he helped raise money for at the high school there, where they have now hosted 65,000 kids over the years, showing them the sky through that dome and the adjacent warm room that he helped make happen. Outreach is the thing that's near and dear to his heart. And while we were up there, he said, if you guys need help putting this together, I'm coming to make it happen. And he's been doing that this week. It's a real gift that he is here helping us. And I think in the next 3 or 4 days, we will have this telescope ready for observing next. And you may have seen communications that we will be having an open house in November, assuming all goes well, and Tom says it will go well. We will have an open house at CAC to show members and celebrate making that thing happen. It's quite an instrument, and it's ours. Yes, we've got a question about this. We might keep it under wraps, but you'll have to talk to the director of the site and see if maybe he'll give you a peek. But it won't be operational then. You might be able to see it. We expect it to be operational because it's got some peculiarities. It's a little more sophisticated than most of the scopes on the site. Yes.
What configuration have you decided on? Optical configuration?
It is in its original configuration. We've talked about possibly reconfiguring the optics of this scope over the years, but there will be separate phases if we do that. The first phase is get it up, get it running, and let's see what we can do with it. That's phase 1, and that is commencing this week.
Mm-hmm.
We'll talk about what might be done later.
So when you get it up and, for dedication time, will it be usable, like at least for viewing?
Classic Cassegrain,
Uh-huh.
usable in November is our goal.
Okay.
Will there be an operator's crew like we do for the 40?
Our intention is to have that same sort of process where all of the telescopes at TIMPA or at CAC are usable by members who are trained to use them. Now, some of the more sophisticated telescopes like this or the 40-inch have higher requirements, but the idea is the same.
Put your hand up really high. You done? Oh, okay.
It's only people pointing at each other. Okay. That's it. Larry? When I left CAC this morning, we were at the point where the operating system was ready to come online. We had strung the cables through this apparatus and brought it out to the control box. It has an unusual mirror cell. The mirror is a relatively thin mirror. It's 1.6 inches, and it sits on a very thin airbag, sophisticated airbag. The airbag is controlled by the control panel, so we had to run all the cabling in order to actuate the airbag. It has to be tested before the mirror is placed in the cell on the bag, and then that mirror cell can be placed on the telescope. The objective is to do that tomorrow. So they were working the controls today. If that all goes well, tomorrow we'll be placing the mirror in the scope, and for the next following days, we'll be getting the scope operational. Be very exciting. Can't wait. Okay, enough of that. It's exciting for TAAA though. Is Eric here tonight? Eric Kokoschka? Eric Kokoschka does our monthly planet report. I did notice that Eric has posted it on the website main page. When you come scroll down, and there's his report. I don't see him here to give it in person, though. We don't have any awards tonight, but we do have one of our AL instructors. Doug, do you have anything coming up in the next couple of months?
So I recently, 2 weeks ago, we had scheduled the star hopping workshop, and I had a number of people sign up for it, but we had to cancel because of weather. It will be rescheduled probably in December, and I'll be announcing a date as soon as I've set a date. So anyone who wants to get into the star hopping workshop, there's still time to sign up. I still have open seats. I've got another workshop coming up in a couple of weeks for constellation locating and finding. And then the fundamentals in astronomy class is scheduled for January. And that one is filling up rapidly. I've only got 5 more open seats. So if you're interested in getting into that one, jump on it now.
Jump on it now. Very popular course. Thanks, Doug. Wouldn't say announcements. I just want to bring your attention to a few things. We have in the back of the room calendars for next year. They are out. They are pretty as usual. They've got all the key dates for 26 in it. Pictures supplied by our members of events and objects and all sorts of interesting things to carry you through the months, and of course all those key dates. So get your calendar. They're at the back table. They are $15, and we can take cash. We can take checks. We can take credit cards. We can take Zelle. And one of those will be yours.
And
We also, again, have merchandise in the back. The merchandise has been going, and want to bring your attention to the website has instructions on getting TAAA merchandise, shirts, hats, coffee mugs, your name tags, that sort of thing. The website has instructions on how you can do it by corresponding with the apparel coordinator. So you can actually get items mailed to you. And if you are going to miss the next meeting, but you really want that T-shirt, we can make that happen through apparel. So check out the website.
the calendars can be mailed too, right, Susan? Susan will deliver in person in town. Wow. Or mail them.
Those of you who want to see Susan, order a calendar, she'll come out and see you. Also want to bring your attention to the fact that we are in a campaign for the Dean Kettleson Observatory to be built out at CAC using the C-14 that was donated by the estate of Dean Kettleson. And the pledge forms are back at the apparel table. You can get a pledge form. The objective is to raise $50,000 to build the observatory. We've raised since the initial announcement last month over $10,000. Thank you very much. So we're on our way, and I encourage you to honor the memory of Dean and help us get another good instrument installed out at our dark site. The existing C-14 is very popular. We can't wait to get another one out there for members to use. One of them is going to be configured for astrophotography with a hyperstar. It's been a long day. I think that's it for various small announcements. Do we have any new members here tonight? Oh, new members. Can I